And
the homework is covering it as well. And it's like nice because I was gonna review this class anyway, but now I actually have like, it doesn't feel like I have a new task, it's just the same task as I have for the other class, but it's also. I feel like I'm finally actually grasping this stuff instead of just like getting enough of an understanding what passive is.
Yeah, I feel like it's acoustic, so it just takes time. To see both acoustic wave equation over $500 time.
There's always something that goes on that makes sense. It's like, oh, there's always a new better.
Let's see physics in the
And also this
form,
book
and then
is
the
way better
simulator
than the other book I've seen yet.
distributes it over time.
Like it actually, I haven't found anything else that actually
Like an
goes over.
interpolation function where it's only on the mesh version. And
Oh,
you're
really?
inside
Yeah,
the
no
mesh
other
is
book, they
defined
just
by-
do A and then they assume that you
A lot of people
understand
just want to
enough
do
of the
those,
graph as well.
You know,
This book actually does the
essentially.
all the other lecture manuals once I looked at did not do that.
Okay.
Sometimes it's limited to like some of the more
Yeah.
advanced books. I remember
I'm doing the,
had a book.
I might do the driving.
He let me see it when we were going through like the partially filled waveguides, and it was pretty helpful.
Nice.
But it was like super dense. I was like, this book is a nightmare to navigate.
But yeah, we got assigned for so long.
Go ahead, try.
What is
Please share with us, I'm like,
What's this homework like?
This one was really cool. It was this one was like MATLAB.
It's crazy.
Oh, numerical.
I imagine that's probably what most of them are like.
Yeah, I don't know what some of the other ones
Did you take it?
It's true. No, I actually haven't.
Yeah. These homeworks are normally very like very, very practical.
Well, I'm good with it.
Yeah.
That's it.
I'm trying to do it with
No, not, I wasn't talking about like, Shakespeare, in general, I was talking about location.
I mean, MATLAB would just be, or I thought it
Because
would just
people
be.
in that area, not just your area, but
It's an animation library.
my area. Sarcastic people. Very quiet.
I mean, I don't know what exactly it's called.
I haven't done GIF, but I've made plenty of like video animations.
I have the question, I won't get it.
Oh, it's fine. It's just, I can't see.
I think he's got the contract there.
Oh, no, he just released.
Turn any video into a GIF. Writing out your file format. It's versatile.
Yeah. That's good. So there's some people like as read.
Or is it in last semester's?
Warren stuff's been
What is?
some big old.
The potentials are in the last semester, right?
So
We studied those. They're in chapter 6 of the book. What's that?
I mean, why we're using it.
Oh yeah, no. That's in this lecture 1 from this semester. Whenever we derive Tm to z or Te to z modes, we pick a particular vector potential with a particular component, so that we can guarantee we get those particular modes that we are trying to derive, right?
you have to just
It says in the slides, you'll see it.
black pipe bubble. Okay.
Yeah, I know that. Good.
Oh, you know what? I might need to make a correction here. Okay, let's go ahead and get started. So you've already noticed, you may have already noticed that we have the homework number 1 up on Canvas now, so you can access that. Before you start it, I need to make a correction here. This frequency probably should be more like 6 gigahertz. So I'm going to change this, all right? Just be cognizant. I'll have a new one up at the end of this class. I'll do it immediately after. But it's going to be different. So if you downloaded it and saved it to your computer before the end of this class, then it's going to change. So I'll send an announcement too to the class, all right? Okay, good. So the first problem, if you guys have taken this class last semester, you'll recognize the format of the problems in the homework. But if you're new to the courses, then what we have here is a couple of problems. They're each worth a certain set of points, 25 points for number 2, for example. Number 1, you need to write down, I didn't write that, but I should probably say that. In your homework assignment that you turn in, you need to write down that I have read chapter 8. That's all, and you get 5 points, right? And the notes. So make sure you write that though, because if it's not there, you don't get 5 points. And number 2, we have TE modes and a rectangular waveguide. You're basically going to go through the derivation so you can understand it from your own perspective, right? And when you're doing things, you can either copy the slides directly, which is fine with me if that's what you're going to do, or you can try to explain in your own words the derivation and do the derivation on the paper, right? So that you know at the end how you got to these particular results, right? And because you're going to utilize those derivations to design a rectangular waveguide that has loss in both the conductor and the dielectric for a particular length in order to incur a certain amount of loss, and for a particular mode, operating mode, TE20. All right. Then you have a problem on MATLAB data visualization. So you're going to make an animation of a vector field in the rectangular waveguide, the TE10 mode. And I thought I'd make it a little fun and have whoever does the best animation, the fancy, and there could be ties, right? But the coolest animation will get a couple of extra points. So it gives you incentive to really sit down and work it out and take some pride in your work, right? So that'll be fun. So that'll be good. And once you're able to do things like this, it's really important to be able to visualize data and derivations that you get, because at the end of your derivation, you'll end up with some expression, but that expression has some dynamic physics behind it, right? So being able to animate parameters or take limits or sweep different things, you'll be able to visualize what that expression is telling you. In this case, you're just learning to write a MATLAB code to do GIFs and animate electromagnetic fields, all right? The dielectric waveguide is problem number 4. You're going to approach that problem in 2 different ways. The first one is by using modes and boundary conditions that we did in the notes. You're going to rederive it yourself, and then you're going to solve the problem again using transverse resonance technique. And that will show you how much paper you use for the first approach and how much it takes for the second approach. It'll be very, very fast, right? Of course, the first approach gives you the fields, the impedance, gives you everything. But a lot of times we just want the dispersion, right? And the last one is a dielectric covered ground plane. You're gonna also plot the dispersion for this, right? Which will be good. All right, so not too bad, I think. All right, you have a week to do it. Let me know if you have questions. I have office hours on Mondays, I believe, just before the course. So that'll give you so if you have questions, attempt it over the weekend, right? And then you'll be able to get questions answered on Monday. Okay. So let's get back into our lecture. Today, we're going to finish up a quick topic in rectangular waveguides with rectangular cross sections, and then we're going to move into circular waveguides that have circular cross sections. We're going to look at all the same kind of geometries, but they'll have a different shape, a different cross section. What that's going to do is force us to use different wave functions, right? The Bessel functions, all of the solutions to the wave equation in cylindrical coordinates. So we'll have to shift coordinate systems. So last time we looked at designing a rectangular cross-section slab. So this is an infinite slab in the XY plane, right? And we went through all of the derivation to calculate the even and odd modes of this particular waveguide, right? So I'm not going to go back through it, but we've concluded that the slab acts as an inductive surface, and it supports both even and odd modes. We did a COMSOL simulation here. We have the odd mode, right? So this is a negative maximum and a positive maximum. It goes through a 0 at the center. And the even mode has a maximum at the center and the minima, if you will, at the edges of the dielectric waveguide. We also noted that the higher the wave number, the longitudinal wave number of this waveguide, the more tightly the confined the fields are. And we can see that in these plots, all right? And we kind of went over a way to model this in COMSOL and do a mode analysis in the cross-section of the waveguide and extract the numerical solutions that correspond to our analytic derivation, our analytic solutions. So this is the next slide in that section. We calculated before what the what all of those quantities were. We solved the dispersion equation at a single frequency at 30 gigahertz, remember? And what we ended up getting is, so here's the example. Let's start at the example, so because the next slide's kind of related. So dielectric slab of polystyrene of half thickness was 0.3175 centimeters, and electrical parameters 2.56 and mu r equal to 1 was bounded above and below by air. The frequency of operation was 30 gigahertz. So if we pick a frequency of operation, then we're going to be able to calculate what modes are supported at that frequency and their wave numbers, right? So A was to determine the Tm to Z modes and their corresponding cutoff frequencies that propagate unattenuated. When they say unattenuated, that means that the alpha in the direction of propagation is 0. Alpha normal to the waveguide is non-zero because it's evanescent outside of the waveguide, right? B, calculate beta yd, alpha y naught, and beta z, and then the ratio of beta z over beta naught squared for the unattenuated modes. So the cutoff frequencies for the Tm to Z modes that are lower than 30 gigahertz, right? The cutoff frequency, what does that mean? That means that if you operate at a frequency higher than that cutoff frequency, then that mode will be supported, right? If you operate at a frequency below the cutoff frequency, then that mode is not supported, cannot be excited. So we know from the expressions for the cutoff frequency that we see right here that when m is equal to 0, this is the expression right here, right? When m is equal to 0, the cutoff frequency is 0. So we always have the TM0 mode, right? That mode has a 0 frequency cutoff, which means it's always there. The first mode happens when m is equal to 1, and that one has a cutoff frequency of 18.913 gigahertz. And we're operating at 30 gigahertz. So this mode is there, right? Good. That's an even mode. It goes odd, then odd, then even for the TM modes. The second cutoff frequency for mode m equal to 2 has a cutoff frequency of 37.825 gigahertz, meaning that our operating frequency of 30 gigahertz is below this cutoff, and therefore that mode is not supported by the waveguide at this frequency. All right, good. So we have two modes carrying our data in the waveguide if we were to use it to transmit information or electromagnetic waves from one point to another. All right, now we calculate what the dispersion is. We calculate the wave numbers, right? So the way we do that is we solve these nonlinear dispersion equations, these ones here. We have this one for the odd, this one for the even, and one of them has a tangent and one of them has a cotangent, and we plot those here. This is one branch of the tangent function, right? This is another branch of the tangent. Then here's one branch of the cotangent and the other branch of the cotangent, right? Okay, so we plot those on a graph that has alpha y naught h as the vertical coordinate, and beta y dh as the horizontal coordinate. And the reason we do that is because these are already written in this form, right? This is like y equals to f of x, but it's alpha y naught h is equal to f of beta y dh, yeah? All right, very nice. Now, these dispersion relations themselves do not have the frequency in them explicitly, right? The frequency is embedded in these wave numbers beta y d and alpha y naught. So we also need to incorporate the separation equations. This one says beta y d squared is omega squared mu d epsilon d minus beta z squared. It is here when we substitute in beta y d for this expression, the separation relation for beta y d, that we get explicitly defined the frequency versus the longitudinal wave number, which is our dispersion, right? So we also need to incorporate these two equations somehow. And the way we do that is we want to plot these two equations on the same graph, right? Which means we need to obtain beta y d. So we need to multiply this by h, that by h, and, well, h squared, I suppose, and then add them together, yeah? Doing that gives you the equation of a circle, and with this particular radius, the square root of this expression is the radius. All right, you plot that then. That radius is a function of the operating frequency, right? Omega. So as we operate at a higher frequency, this circle will become greater and greater. It'll intersect more of these tangent curves, and there will be a solution to this sort of four equations that we're solving kind of simultaneous, and therefore higher or more and more modes, right? Okay, good. So how can we excite more modes, right? There are multiple ways. Operate at a higher frequency, make it thicker, yeah? Or make the material parameters greater. All right? Good. So once we do that, for our example here, we have to plot first the tangent curves. They're here, right? What do we need as input for the tangent curves? We need epsilon naught over epsilon d, right? This is an ordinate or a coordinate, and so is this. So we're just plotting tangent and cotangent on this particular set of axes, but we need these scale factors, epsilon naught over epsilon d. And in this particular example, epsilon naught over epsilon d is 1 divided by 2.56, right? Okay, good. Okay, so we plot that here on this graph here, and the first thing we do is then we go read all these intersection points. Here's one, right? The first one is the Tm to 0 odd. Then we have the Tm1 even, and then this curve, if it had an intersection point, would be the Tm 2z odd, right? Okay, so we have two modes, Tm to 0 odd and Tm1 even, all right? So that for the Tm to 0 odd mode, we go here, this intersection point, we can read off directly what these values of the coordinates are. And the first one appears to be 1.329 and 2.108, which is here and here. Divide both sides by h, you get your dielectric wave number in the vertical direction and the once you have one of the wave numbers, especially in these 2D problems, right? There's only one independent wave number in a 2D problem. For example, beta x squared plus beta y squared plus beta z squared equals to beta naught squared, which is omega squared mu epsilon, right? So if I know my operating frequency, which I do, and my material parameters, then this number's fixed, beta naught, right? How many of these wave numbers are independent? 2, right? The third one has to be, you have to add beta x, beta y, you can choose at will. Beta z has to add to these two chosen values in order to sum up to beta naught, right? So they're only 2 independent. If the problem is 2-dimensional, then one of these wave numbers is also 0, right? And in this geometry, let's see, there's beta z and beta y, right? Beta x is, let's go back to the geometry. Beta x is 0, right? We can see it here. So we have a beta y and a beta z is equal to a beta total, right? Beta naught, there's a z and there's a y. So beta x is 0, yeah? Because the geometry is infinite in this direction. These little wavy lines mean that this continues on forever. So there's no variation in geometry in that direction, therefore the wave number is set equal to 0. Okay, good. So there's no beta x. So what does that mean? That means that in a 2-dimensional problem, we have beta y squared plus beta z squared equal to beta naught squared, for example. And what that implies is there's only one independent wave number. So what I'm trying to get at is, once I find one of the wave numbers, then I have everything, right? So I found beta y from this. And I can find easily beta z, so everything I said can be summarized in this one equation. So I probably said too much. But anyway, beta z, now we can find beta z. So we have both the wave numbers, right? Beta z is 917.4 radians per meter, and then this quantity here. And for the Tm1 mode, you do the same thing. You read off the values from the graph, beta z. Of course, if you were to design this, you wouldn't use a graphical approach, right? This is probably before computers were, it's to give you insight. You know, changing the frequency, change the radius, then I can find what modes will be excited, and it kind of gives you a graphical illustration of what these equations are. But if you were to design a waveguide like this, you probably wouldn't use a graph, right? You would use a computer and solve these equations in MATLAB or something. But anyhow, the one mode has 685.7, right? Radians per meter for beta Z. So we did the analysis validation, but we did all of that at one frequency, right? This radius had only a single radius at a single frequency, omega. And we picked up the modes that were there at that frequency. Sometimes you want to solve these four equations not at just a single frequency, but as a function of frequency. So before, at 30 gigahertz, each of these modes had a well-defined z-directed wave number, right? So the wave number and the z direction's fixed for these two modes at that frequency. But dispersion is typically a plot of the wave number versus frequency. So these are the full dispersion curves now. So here we're solving these four equations, but now as a function of frequency, right? On the x-axis, we're plotting the normalized frequency, which is f divided by the cutoff frequency for the first mode. And that frequency for the first mode was 18.913 gigahertz. All right? So at this point, which is halfway between 0.8 and 1.2, which is this point, that's 18.913 gigahertz, right? Because f divided by fc1 is equal to 1. All right. What do we see here on these plots? We see beta z, alpha y naught, and beta y d, and then this quantity, that square, that ratio of wave numbers, as a function of frequency now. And we can see the dispersion, right? So if we operate at a particular frequency, let's say, for example, the 30 gigahertz, right, is this red line that I put on the plot. That 30 gigahertz is the one we already solved. And we got 9.14. This is in terms of centimeters, right? The units aren't here. I should probably put those, but this is radians per centimeter, right? All right. And that's what we already solved, right? But now you can see if you operate at a different frequency, that longitudinal wave number changes, which is important, right? Because let's say that you want to design a waveguide that has a delay line, right? You probably wouldn't use this geometry to do that. But if you had a microstrip patch antenna and you wanted to design a delay line in its feed. So here's an example. If you have 4 patches, you want to make a little 2x2 array of microstrip patch antennas. You might come in like this and feed this one and this one, right? And then you might go, okay, this needs to be a little more accurate because these lines matter. Here, 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 here. I go here like that and like that. What's wrong with this thing? Anybody have an idea? What? These are all the same length. All right, assume these are microstrip lines, and I feed all these patches. They all have the same length. So they're all, so the line length due to the phase due to the line length is all there, right? It's all the same. What's wrong with it? All right, yeah, so, oh, yeah.
The patch on the left side and the patch right side is out of phase.
Excellent. Very nice. Very good. The polarization is the opposite, right? So if you come in here, you're going to excite the current going this way. You're going to excite a current going that way. And if you come up into this one, you're going to excite a current going that way. And they're 180 degrees out of phase. So how do you fix it? The way you fix it is you add a delay line, yeah? So you need a 180 degree delay before this patch. You go here, and this one you can maybe add a little loop. That loop has an extra 180 degrees of phase, all right? Okay, so to design this, you need to know exactly what beta Z is, or beta in the direction of propagation of that microstrip line, right? You need to know exactly what the beta is, so you can find the exact L that gives you a 180 degree phase, right? So beta is important when you're designing transmission lines and waveguides. That's the quantity of interest. But look at what happens here. What's wrong with this? This line is exactly 180 degrees at the design frequency, right? If I were to use a dispersive transmission line to design this, then well, anyways, if I shift frequency, this is not 180 degrees anymore. But even if, okay, so this example has like a two problems, right? Assume that it was still the same length at a new frequency, but the line is dispersive, then at a new frequency, the wave number is changing. So if you want to design this for, multi-frequencies or whatever, or have some bandwidth, then you have to consider the dispersion. And you need to know how beta varies with frequency, right? Good, all right. Okay, good. So anyway, that's an important plot here, right? So it shows you the dispersion of beta with respect to frequency. And this is for the TM1 mode, all right? And to get dispersion, you need to solve the dispersion equation. All right, so transverse electric modes, it's all exactly the same for this dielectric slab, except the only thing that's different is this that I've highlighted in red, all right? And I think this one was a cotangent before, or tangent before and became cotangent. There's very little differences, right? But now, what do we see here? What do we need, right? I suppose if you had a dielectric that had mu d equal to 1, or mu r d equal to 1, then you could still solve this, right? Yeah, so, okay. So now you need to specify the magnetic properties. It's the magnetic properties that affect the dispersion of the TE to Z modes for the dielectric slab, all right? It's interesting because what we derive here is, look at this. This is the expression for the wave impedance. Before, what did we find for the TM modes? And this is common across a lot of waveguides, sheet impedances and all that. Let me see if I can find here. What did we find? We found that for TM modes, the waveguide is inductive. The sheet impedance, or the input impedance looking down into this slab from above it, is an inductive impedance, the wave impedance rather. Yeah? For the TE modes, we find that it's capacitive. All right? Very good. Whoops. All right, so let's look at a dielectric covered ground plane. This is something that you will definitely come across in your research, right? Because whenever we have microstrip lines or patch antennas or any kind of printed circuits, they're usually on a dielectric that's grounded below, right? So this is a very important structure to study. Consider the dielectric covered ground plane waveguide. The field's inside the dielectric for y less than or equal to h. So we're talking about inside of the dielectric. Let me describe the geometry here. So we have the same thing we had before, but before we had a slab that was of thickness 2h, right? This is also h. And we defined this as 2h. And this is exactly why we defined it as 2h before instead of just h, because we were going to cut it in half later. All right? So we have a slab over a ground plane that has a thickness h, or a height h, above the ground plane, and it has epsilon r, mu r as its material parameters. It's still infinite in the z and x direction. All right? So for y, absolute value of y less than or equal to h, we can obtain the solutions for the field inside the dielectric from our previous solutions for the dielectric slab waveguide, right? They'll be exactly the same. All right? So these are the solutions from before for the TM to Z odd modes, right? Let me show you that. So before, we had the TM to Z odd modes, and TM to Z odd, where did we put the fields? Example, and TM to Z, here. So the electric field is here. These are for the TM to Z even modes, all right? For the even modes, we had Y. For the even modes, we had the Y component was a sine and the Z component was a cosine, right? So let's go here now to the even modes of this structure here. And what do we find? The same thing, right? The even modes, we had sine and cosine. I might have labeled these wrong. I think I labeled these wrong, okay? Yeah, this one should be even, and this one should be odd. Let me correct that. Let me take a look at this. Yeah, when we're discussing the even and oddness of the mode, it's the y dependence, but is it the z component or the y component that matters? Let me go back and correct that. So recheck your notes later, but I think I labeled these wrong. But anyhow, these are the exact fields from the dielectric slab of thickness 2h, all right? And if you go back and correlate these solutions, you'll be able to determine if it's named incorrectly. So what we can observe is only the Tm to Z odd and the Te to Z even modes satisfy the boundary condition, the new boundary condition to the ground plane at y equal to 0, right? Tangential E has to go to 0. So let's take a look at which modes satisfy that. So the Tm to Z odd modes, no, these are correctly labeled. I'm pretty sure this is correct. But I think this subscript bothers me. I call this an odd mode, but then I subscript even. There must be a typo. All right, I'll fix it. All right. So at Tm to Z odd, a tangential E has to go to 0, right? So what is tangential E? That would be EZ and EX. So EZ, cosine of 0 is 1. So this is incorrect. Tm to Z odd. Yeah, these are labeled backwards. Swap these. So this is the Tm to Z odd. Yeah, they're backwards. So this odd mode, EZ, is tangential to the PEC and is sinusoid. So at y equal to 0, this goes to 0. And it doesn't have an EX. So this Tm to Z odd, yeah, these are definitely backwards. That's the error. This should go here, all right? And this as well, okay? And the other mode is the Te to Z odd, right? Te to Z even. Why? Oh, but the labels are backwards, of course. Yeah, these are the evens. All right, so these ones are good, and so are Tn to Z odd is this one. I don't want to circle the labels because they're backwards. These ones are good, and these ones are good, and these labels are backwards. All right, so it's super confusing. Anyway, the sinusoids, the ones that have sinusoid in the tangential components, they have to go to 0, y equal to 0. Cosine of 0 does not go to 0. So that's how you can tell. All right, good. All right, so that means that the dielectric covered ground planes support only modes that are Tm to Z odd or Te to Z even. Very well. All right, so the governing equations for the Tm to Z and Te to Z even modes, Tm to Z odd and the Te to Z even modes from before are these, right? So this was the dispersion for Tm to Z odd. This was for Te to Z even. These are the same for all of them, and so is this, right? Except the indices now run like that. So use the same approaches to solve the dispersion relation for the dielectric slab that you used to solve the dielectric covered ground plane. You're gonna do that in your homework, right? Very nice. I don't know if I will go into this other topic here. Yeah, let me skip that. All right, so let me get the, we're gonna skip the surface plasmons. Maybe we'll come back to that. So let me pull up the new lecture, lecture 2. Taking forever. Okay, so yeah, this is still still trying to close this. Maybe I'll just kill it. All right, there we go. All right, so here and here, there, there. All right, good. All right, so we finished that chapter on rectangular cross-section waveguides. All right, now we're going to move into circular cross-section, waveguides that have circular cross-section. So this is the next lecture on circular cross-section waveguides and cavities. And as usual, the references that I used to create the slides, and we'll get right into it. All right, so what's going to be different? We're going to study all the same things, right? We're going to study rectangular hollow pipes, or sorry, circularly cylindrical, circular hollow pipes, circular cavities, and we're going to study dielectric rods that are of circular cross-section, and then we're going to study a metallic rod with a dielectric coating around it. All right, all the exact same things we studied just now, but in cylindrical coordinates. So the first thing is a circular waveguide. We're going to look at TE to Z modes first. To derive the TE to Z modes of a circular waveguide of this geometry, where we have X, Y, Z like this, Z is the axis of the cylinder. We have cylindrical coordinates now with radius rho, angle phi measured from the x-axis, and the other coordinate is z. This is a circular waveguide that has radius a and has epsilon mu material filling inside of it. To derive the TE to Z modes of the circular waveguide, we follow the same general procedure. So since we want TE to Z modes, so here's the answer to your question. We want TE to Z modes, meaning that the electric field should be transverse to the Z-axis. How do we get modes like that? There's a way we can use the vector potential formulation to guarantee that the solutions that we derive using this apparatus have TE to Z characteristic, meaning the electric field is orthogonal to Z, or it has no Z component, in other words. So what I do there is I set A equal to 0 and choose an electric vector potential that has a Z component only. All right? In doing that, I know to get D, I have to take the curl of the negative curl of F, right? And the curl is orthogonal to the axis of which the field that you're taking the curl of points. All right? Because it circulates around that axis, right? Okay, good. So that's how you get TE to Z modes. So this function F has only a Z component, and it's in cylindrical coordinates, rho, phi, and Z. It has to satisfy the homogeneous vector wave equation. And we solved this last semester. And this is the expansion for just an FZ for this equation here. We take the Laplacian and cylindrical coordinates, and we get this expression. We solved this equation last semester. And for the geometry above, we found this general solution that has the right wave functions for this type of geometry. What do we have? We have A1 Jm beta rho rho, right? This is a Bessel function of the first kind of order m. It has a radial wave number beta rho and an unknown coefficient A1. Then we have the Bessel function of the second kind of order m, which is an evanescent mode, right? I guess it's not evanescent, but it's non-singular at the, or it is singular at the origin. B1 Ym beta rho rho, right? This is not an evanescent wave, this is a standing wave, by the way. And these are standing waves in rho. Why did I choose these two functions? Remember, what is the functional set? What are the wave function solutions for the wave equation cylindrical coordinates? What are the wave functions that we get? You get Hankel, right? So what are all the solutions? What are all the possible solutions? Do you remember? There's Bessel function of first and second kind. These are for standing waves. They represent standing waves. And remember, y is singular at the origin and j is finite, right? And the other ones in rho were what? The Hankel functions, right? Hankel 1 and Hankel 2, Hn1, Hn2. Hn1 represents converging waves that are converging toward the origin, a cylindrical wave converging toward the origin. And Hn2 represents diverging radial waves or diverging cylindrical waves that are emanating from the origin. And we also had the I and the K, which are the evanescent waves, right? But I think they call them maybe fourth kind Bessel functions. All right? Then we know in cylindrical coordinates that the wave functions have to be periodic in phi, right? Because if you go around phi to pi, you come back to the same point. That means the field has to be the same there, which means that the wave functions have to be periodic in the azimuth coordinate. So what we have there is cosine and sine. Cosine m phi, sine m phi, right? All right. And we have traveling waves in this situation in the z direction because it's unbounded. So we have e to the minus j beta z and e to the plus j beta z. The separation equation here was beta rho squared plus beta z squared equal to beta squared. What happened to the third? Do you guys remember what happened to the third wave number?
Coupled with one of them.
Very good. That's right. There were normally three, right? But look, the third separation constant that we derived from separation of variable solution of the wave equation cylindrical coordinates was m, right? M is the azimuthal separation constant. But if you look at the way this is written, the radial wave functions have the m in them as well. So they're linked, right? By nature of how we had to solve the differential equations. So the M appears, it's linked. M links the azimuthal order and the radial order. All right, good. All right, so we find the coefficients in wave numbers by applying the boundary conditions again. Now our boundary condition is E phi. Why do we only have E phi? As tangential components to the metallic walls. Very good. TE to Z. There's no Z. Z is the other tangential one. Rho is normal. So we only have E phi at rho equal to A has to equal to 0. The fields must be finite everywhere, right? Can't have infinite fields. So for the fields to be finite everywhere, Ym has to be as excluded, right? That means B1 has to be equal to 0. All right, so we know that immediately. And the fields must repeat every 2 pi radians in phi. That means M has to be an integer. All right. Okay, good. All right, so let's consider waves that propagate only in the z direction again. And what do we get? Our electric vector potential with the z component is equal to AM and JM beta rho rho because we got rid of YM because the fields have to be finite everywhere. C2 cosine M phi plus D2 sine M phi. And M is an integer because the fields have to be periodic. And e to the minus j beta z only now because we're considering waves that propagate only in the plus z direction. All right, so now we have to apply the remaining boundary condition that E tangential has to go to 0. So we have E phi. We have to calculate E phi first, right? So E phi is 1 over epsilon partial fz plus over partial rho. These equations come directly from the definitions of the vector potentials, right? The curl of f has to d is equal to the negative curl of f, right? Or E is equal to negative 1 over epsilon curl of f, right? All right, so this is part of the curl, the phi component part. Okay, well, we have to differentiate our f with respect to rho. So that means Jm picks up a prime, right? This is Jm prime, and this is Jm. Jm prime is the derivative of the Bessel function, the nth order Bessel function, when you take the derivative with respect to its entire argument, all right? And remember this from last semester, we had explicit formulas on how to do that. They're also found at the back of your book, all right? Okay, so let's do the differentiation. We did that here, Jm prime, right? Now we need to evaluate E phi at rho equal to A. So we're going to plug in rho becomes A, right? So rho equal to A. All right, now this has to equal to 0, right? How can we make it equal to 0? We make it equal to 0 by ensuring that this function, Jm prime beta A, goes to 0, right? Because it's a boundary condition in rho, and the only function in rho is this one, right? Okay, so we need to find the zeros of the first derivative of the Bessel function of order m. All right, fine. So that means we're going to say beta rho, which are the coordinates, the cylindrical coordinates, the argument of this Bessel function has to equal to some number, which we're going to figure out what that number is. But if beta rho A is equal to this chi mn prime, then that makes the Bessel function first derivative go to 0. All right? Okay, and from there you can find the radial wave number, beta rho. Now, let's look at these zeros, right? So what are these xmn's? These are, or chi mn primes. These are tabulated in this table. This table shows you the zeros, which are these numbers, right? The argument of the Bessel function. What arguments of the Bessel function give you a 0 for the derivative of the Bessel function of order m, right? Jm prime. All right, and so these orders they're indexed with m and n, right? So first we have m equal to 0, 1, 2, 3, 4, 5, and so forth. And then we have n equal to 1, 2, 3, 4, 5, all right? All right. So these m's are indexed in that way. What does this mean? Well, what is the order of the Bessel function itself? M, right? So this first column, m equals to 0, corresponds to J0. And J0 has a bunch of zeros, right? Well, there's a bunch, there's infinite number, right? So these are the first 5. So what I've made here is a plot of J0, which is the dashed red line, this line here. and its derivative in the solid red line. All right. And you can see, so here, look, right at this point, J0 has a 0 slope, right? So you start off with the derivative being equal to 0. Then J0 slopes downward, so it has a negative. So it has a negative derivative. And at some point, where's J0 here? J0 crosses 0, right? Okay, so that's when it has the maximum slope. Then it starts to curve back, right? And at this point, J0 has a 0 derivative again. And you can see the derivative curve goes through a 0 right there too. All right. Okay, so here's J0, J1, J2, and these are primes of these, right? All right, now, the ordering of these modes is shown in this table. So you start with the lowest one, right? The lowest one is 1.8412. So the very first mode that appears is it's going to be the TE11 mode. That's how these are defined or labeled. The next mode is TE21, right? Then TE01. All right? So the lower the number, we'll see that. The cutoff frequencies are in the next slide. So maybe I'm jumping ahead. All right, good. So now that we are able to calculate what beta rho is using these zeros, then we can easily calculate what beta z is. Once we have beta z, we can find the cutoff frequencies. Because when beta z goes to 0, that mode is not propagating anymore, right? So we can now define beta z from the zeros of the derivative of the Bessel function. So here's beta z. We found beta rho from the zeros. Beta rho is equal to chi prime mn over a. And this is the wave number beta z when beta is greater than beta rho. That means beta z is a real number. And then we have e to the minus j beta z as the wave function. So it's a traveling wave, right? Here, when beta equals to beta rho, when beta is equal to beta rho, we call that beta cutoff. And that makes beta z equal to 0 exactly, right? So when beta is equal to beta rho, which is chi mn prime over a, then we get a 0 beta z. That's exactly a cutoff, right? That's why we call it beta cutoff. So we can find the beta cutoffs from this expression. Then of course, these are the evanescent modes. When beta rho is greater than beta, then you get this minus j coming out. And then you have e to the minus j beta z times z, but beta z is minus j alpha, so then you get minus alpha z, evanescent. So cutoff occurs right when beta z is equal to 0, and we said that happens when beta cutoff is equal to chi prime mn over a. But beta is omega squared of mu epsilon, and we're looking at the particular omega cutoff, which is 2 pi f. And then we set that equal to chi prime mn over a, and we can find the cutoff frequencies now are proportional to chi prime mn, right? So the smaller chi prime mn is, the lower the cutoff frequency, right? So the lowest value in that table is the first cutoff frequency, meaning that's the first mode that appears. Yeah? All right, and how can we modify that? We can change the radius or the material parameters filling the waveguide. Okay, so let's go back to the table now. We know that FC mn is chi prime mn divided by 2 pi a squared of mu epsilon, right? So here, look, this is the lowest value in the table. That means the first cutoff frequency is when this value is 1.8412. And then they're ordered, and that is the TE, and then the modes are MN, right? So this becomes TE 1, 1 is the first mode.
What is n? How did you?
What's that?
What is n here?
N? Okay, so the Bessel function has an order M, right? So there are many Bessel functions in the expansion of the field, right? So technically, there's a summation over infinite number of Bessel functions, right? All right. Now, so this column here is m equal to 0, which is the J0 term, right?
These are all the zeros of J0.
Yes, so this column is J0 because it's JM. So this is J0 column. And there, J0 has a bunch of zeros, right? There's one here, there's one there, there's another one there. J0 has a bunch of zeros. As the first 5 of them, n equal to 1 to n equal to 5 are shown. Yeah? Okay. Great. So we'll do an example. So we can
right? You only showed the first 5.
yes, there are infinite zeros of the Bessel function. Yeah, there's a bunch of them, right? But okay, so you're not going to have like the TE 1005, you know, there you'll probably only have a couple of these modes. All right. So with this definition, we can write beta z in terms of the ratio of the cutoff frequency and the operating frequency. Same we did for the rectangulars, right? So we have beta rho here. We can factor out the beta squared basically. Then we end up with this expression, right? Now we can say at the cutoff frequency, we want to introduce the cutoff frequency. So we say beta rho is equal to beta c. All right. And then from there, we know what beta c is, right? Beta c is chi prime mn over a. So that's here. Good. And then we can relate this to fc over f by doing 2 pi or omega squared of mu epsilon, and everything common cancels, right? And this is now beta z as a function of frequency for each mode, right? The cutoff frequency of each mode. This is the mnth mode. Each mn mode will have a different fc. All right, good. Okay, so knowing beta z, we can find the guide wavelength. Okay, that's obvious, right? So lambda beta z is 2 pi over lambda z, and lambda z is the wavelength of the mode, the distance you have to go for the mode pattern to repeat in 2 pi phase in the z direction. So then you can find, once you have beta z, which is solved for before, we can get the guide wavelength, all right? All right. And then you can find all the fields, right? These are directly from the definition of the vector potentials and Maxwell's equations. So you can find all the field components. Good. All right. What do I want to say about these before we move on? Let's look at an example. Cool thing about mode impedance is the same as for the rectangular waveguide, all right? In this case, for cylindrical waveguides, we have E rho over H phi, because rho cross phi gives me Z, all right, in the direction of power flow. Or we have E phi cross rho because phi crossed with rho gives me negative Z, so we need to negate it. That's equal to omega mu over beta ZMN, right? And you get the same exact expressions as you did for the TE modes in a rectangular waveguide. All right? What can we observe? Above cutoff, so here's cutoff, right? F over FC. F is the variable. FC is a known value for each mode. Then right at cutoff, we see that this is equal to infinity, right? Oh my goodness. Okay, it's equal to infinity. So it goes off to infinity, right? We're looking at TE modes here, the solid curves. And goes to infinity. And below cutoff, it acts as an imaginary inductive. And above cutoff, it's real, right? You want the wave impedance to be real because that is associated with real power flow. If you calculate 1/2 real part E cross H conjugate, and you have an imaginary wave impedance, or in other words, E and H are out of phase. If they're completely out of phase, 90 degrees, then you get, then you'll have no power flow, right? And it'll be reactive. So the wave impedance kind of tells you if it's imaginary, then it's going to be reactive power. If it's real, then it's going to be associated with power flow, right? Okay, good. Let's do an example so we can understand everything. A circular waveguide of radius A equals to 3 centimeter is filled with polystyrene with an epsilon R equal to 2.56, and it is used at a frequency of 2 gigahertz, all right? For the dominant TE to Z, TEZ MN mode, determine the following: the cutoff frequency, the guide wavelength in centimeters, and compare that guide wavelength to the infinite medium wavelength lambda. Find the phase constant beta Z, radians per centimeter, wave impedance, and the bandwidth over single mode operation, assuming only TE to Z modes, right? So you want to find over what band of frequencies can we operate this waveguide at where we only have one mode, the TM mode, all right? We'll see that's fixed for the cylindrical waveguides. The dominant mode is the TE11 mode, right? So here are the zeros of the Bessel function's derivative. The dominant mode is the one with the lowest chi-mn, which is TE11. This is a 1, this is a 1. TE11. So the first mode that appears is TE11. And that cutoff frequency is you take this value for chi-mn and then you plug in 2 pi a square root of mu epsilon. What do you get? 1.83 gigahertz. That mode is there. We're operating at 2 gigahertz. We're above the cutoff frequency. So that mode is excited, right? If we operated at 1.5 or 1.8, nothing would be, the waveguide wouldn't carry energy at all. Everything's evanescent at this radius, right? All right. FC21 is the next mode, right? Because this is the next higher order number, or the next lowest number, which is 2, 1. So let's check TE21. If we do the calculation with 3.0542 here, what we find is 3.038 gigahertz, and we're operating below that cutoff frequency. So that mode is not excited in the waveguide or supported by it, right? Excitation and support. All right, so the waveguide is operated under a single mode, is what we've concluded if we operate at 2 gigahertz. The guide wavelength, we need to find that, which is lambda over the square root of 1 minus fc over f squared. We calculated that in the previous slide, right? But lambda here is, it's not filled with air, right? It's filled with polystyrene, so don't forget to do that. You always have to take your material parameters into consideration. Lambda naught divided by the square root of epsilon r to get lambda in the medium. Okay? Then you get 0.2334 meters. We know the cutoff operating frequency F and the cutoff frequency for the TM1 TE11 mode. All right? All right, so I went to CST and did a bunch of simulations. We'll show you. The phase constant in the direction of travel, we need to find that. Once we know beta, FC, and F, we can find beta Z easily. 2 pi over lambda, right? But remember, this is the lambda in the dielectric, so don't forget about that. We end up with 26.92 radians per meter, and the wave impedance for the 1-1 mode, why is this in H? I don't know what that is. I think we need to, you think that's a typo. 586.56 ohms, all right? This is important, right? You need to match to it. You need to feed the waveguide. Okay, the bandwidth. So the bandwidth over single mode operation, what does that mean? What range of frequencies can I operate this at? You know, what is the bandwidth, right? The relative bandwidth of 2 to 1, 3 to 1, that kind of bandwidth for a single mode operation. Well, the next mode appears on chi is this, and the first mode appears on chi is that. If you divide the two equations, everything drops out but these two. So you ratio these two numbers, and you get 1.65 to 1 bandwidth. And you can't change that by changing the radius or anything. The radius canceled out, right? Bandwidth is fixed. No matter, I can't change the radius of the waveguide or fill it with different materials to get different bandwidth out of it. All right, here's the first mode from CST. We operate at 2 gigahertz. It's a TE mode. The wave impedance that CST calculated was 579, which is kind of close to our 586. And the beta was 26.93, which is close to what we have, 26.92. And this is the mode plot, right? So what do you notice about cylindrical waveguides first off? Okay, yeah, this mode has that kind of amplitude distribution. But one thing about a cylindrical waveguide, there's a bunch of degeneracy in it, right? Not a bunch of degeneracy, but there's a bunch of ambiguity. I don't know how to word what I'm saying. I'm saying you can rotate this electric field any angle phi and you still have the right solution, right? So you have to define, when you do this simulation in CST with these cylindrical waveguides, because of the azimuthal symmetry, you have to define the direction you want the electric field to be in for the first mode and for the second mode, all right? So that you have to do in CST, and I did that. So I said the first mode I want to be in this direction, all right? It would have given me all these same numbers, but it wasn't guaranteed that I would have a horizontal field profile. So the electric field here is TE, right? So what does that mean? This is the cross-section of the waveguide. This is all of the electric field, right? This vector field plot. There's nothing in and out of the board. There's no components in and out of the board. So it oscillates back and forth like that in time. All right? And we see a maximum at the center. Now, what's not shown here is it's not perfectly x directed, right? Why can't it be x directed perfectly? Let's see if you guys can pick up on that. Not fringe, right? Everything's contained here.
Tangential electric field.
Excellent.
Boundary must be zero.
That's right. Very good. Good job. If it's purely x polarized like this, then at some point I'm going to end up with fields that have a normal component, right? This x directed field here can be decomposed into a normal and sort of a tangential component there, I suppose, something like that. But anyway, over here, if it's purely x polarized, here's the normal. Here's the, let me do it that way. Here's the normal to the waveguide. Here's the tangential. If I come in with x, so to say this is my E polarization, right? This has a tangential component, and that can't be. So what does it look like? It looks like this, really. It has to be normal everywhere at the PEC walls, right? Yeah? All right. And you can kind of see that if you look close. You guys probably can't see from there, but it curves like that. All right? Very good. Okay. So what do they look like? So cool thing about CST, it gives you all these animations, yeah? So here is the first mode, which is, oh yeah, this is what I'm plotting. This is the electric field of the first mode, right? The same thing we saw on the last slide. Here's it in 3D along a waveguide of a particular length, 3.5 lambda, I believe. And you can see what it looks like. So the maximum, the minimum, and that thing travels down the cylindrical waveguide, exactly like the rectangular waveguide, but the mode shape is a little different, right? Because now we have to have these curved vector fields in order to have zero tangential E in the waveguide, right? So it looks like that. But it travels down the waveguide similarly, right? Just the mode shape's a little different. It's described using Bessel functions rather than trigonometric functions. Here's the magnetic field over here. So the magnetic field here has components in and out of the board and components in the board. And it looks like this. And if you look at these, they are so the way that the mode is set up, when this is a maximum, this field is it's kind of not going through its zero. I don't want to say it like that because that's more like a cavity. The energy is not being exchanged between electric and magnetic fields, but the way that these modes are, this maximum here is associated with the gap between two maxima of the electric field. Same as the rectangular waveguide. If you go back in, you can see that. All right? So don't think of these things oscillating 90 degrees out of phase. That'll happen when we make a cavity out of it. All right. Okay. Let's look at TM to Z modes. Do the exact same thing, right? So we could probably go through this quickly. For TM to Z modes, we want the magnetic field to be orthogonal to Z. And we know that B is equal to the curl of A. And the curl is orthogonal to B, which is the curl of A, is orthogonal to A. And we want M to be orthogonal to Z. So we choose A to have a Z component only. Yeah? And no F. Okay. Oh, man. See, copy and paste. So this is an A. Whoops. A must satisfy the homogeneous wave equation here. And this is expansion in cylindrical coordinates. And we saw this equation last semester. This is exactly the same, right? As we just had before. Nothing different between A and F here. Okay. So, but now the boundary conditions that we need to solve are E phi equal to 0 and Ez equal to 0. Why is that? Yes. And now we have a Z component of E now, right? Because it's TM mode. All right, same two conditions for the finiteness and periodicity. All right, so consider waves that propagate only in the Z direction again. So now we have only E to the minus J beta Z. And now we got to find the electric field to apply the boundary condition. But this expression is different than we had for the TM mode or TE modes, right? Now what we get is this expression here for EZ. And we differentiated the Z, not the rho, to get the E, right? So what do we have? We have Jm now, and therefore, when we set this equal to 0 and evaluate it at beta equal to A, then we have to look at the zeros of Bessel itself, not the derivative of Bessel for this mode set. All right, so this table is different than the one that we looked at before. This table is the zeros of Jm now, not Jm prime. All right, so here are the mode orders. They're different. This is Tm modes now. So Tm01 is the first mode. Then Tm11 is the next mode. Then Tm21 is the next mode. Then probably Tm02. Yeah? All right. Good. So same exact equations here, right? So we get beta z now. Beta z is exactly the same as it was before, except now instead of prime here, we have xm, just xm, right? Or chi-mn, right? No prime. But they come from the table, the same as before. You just use a different table now. Same thing with the cutoff, and same thing with the beta z in terms of the cutoff and the frequencies, cutoff frequency and the frequency of operation. All right, now we can find lambda g in the same way. Here are the field expressions. These field expressions are for the Tm modes. So you see these electric fields are different, right? These ones are simpler, right? These come from the curl. Then the electric fields come from the curl of H, right? Equal to minus 1 over j omega mu into E, right? Or I think I said that right. So here you would get B is equal to the curl of A, and then you would want to find E, so you'd have to take the curl of H, and that's equal to j omega epsilon E, right? So then if you want E, then you find it as the curl of H divided by j omega epsilon. And you have H because H comes from, you can say H is 1 over mu the curl of A. And A we had, right? Okay, good. Mode impedance is the same as the Tm modes in a rectangular waveguide. Now we have eta multiplied by this factor instead of eta divided by that factor. And in this case, at cutoff, the wave impedance is 0 instead of infinity. And in this case, you get capacitive below cutoff. All right, so it's capacitive below cutoff. It's the dash line now. And you get 0 at cutoff. Good. So what do the mode field plots look like, right? We already looked at this one, which was TE11, right? So the electric field is a solid line, and the dashed line is the magnetic field. So what do we see? This electric field has this exact shape that we were talking about, right? Has to be normal everywhere to the walls. And the magnetic field has sort of this shape where it's stronger here, and then it sort of circulates, right? But it has a component in and out of the board. Here's Tm. Now Tm01 is going to have the magnetic field purely in plane. No Z component magnetic field. That one forms rings, right? Tm01. Then you can have Te21 here. So these kind of get, pretty cool looking. So you can go through all of these mode patterns and try to understand them yourself, right?
It's no TE0.
Te01 is here.
So TE11 occurs before.
Yes.
Okay.
Yeah, you got to go to that table and find the order of the zeros of Jm prime if you're talking about Te, or Jm if you're talking about Tm. All right. Very nice. Let me see what else we got here. The electric field of Te01 are rings, yes, because Te has to be transverse to the direction of propagation. So this one is kind of the dual of that one, if you will. There are rings of E in the magnetic field. Okay, so let me ask you a question here. Te01, right? So we can have an electric field that's transverse to Z and then forms these rings, right? Okay. What does the magnetic field look like it's doing? Okay. But what do you know about magnetic field lines? They have to be closed loops. So really, and this is a TE mode, so there's a Z component magnetic field. So these are longitudinal loops.
Yeah, but why the electric fields are closed loop?
The electric fields, they form, yeah, they can, the electric field can form a closed loop, right? When is the electric field able to form a closed loop? Electric field? So remember, what is the the divergence of D is equal to rho, right? So when it's a closed loop, what does that mean? No charge is correct, right? Or basically the divergence is equal to 0 because divergence of B equal to 0 tells us that there's no sinks or sources of the B field, right? So they have to be closed back on themselves. But anytime I'm at points where there's no charge, then divergence of D is equal to 0, and that also forms closed loops back on themselves, right? These are modes in the guide, right? This is supported by the waveguide away from the source. So these are, we solved the homogeneous wave equation to get these, right? So after the source launches the fields inside of the waveguide and they start to propagate, at any point away from that source distribution, then you can expand the electric field in terms of weighted superposition of TM and TE modes.
That's the case. The other modes should have that too. As well. No?
What is the same about the current on the surface?
Okay, well, let me answer this question really quick. So there are two situations here. The first one is these rings, right? These are rings of E and they're forming closed loops, which means there's no charge for those loops to terminate on, no divergence, right? Or convergence, or no sources or sinks of E in this modal profile in the cross section. All right, but what is the other boundary condition that would require charge? Remember the boundary condition N dotted with D is equal to rho surface for this conductor. So what is the normal component of E here, or basically epsilon E? Then yeah, and this has only phi. So there's no charge here. So this is okay, right? But this pattern over here, this one has endpoints, right? It has normal components. So there is charge on the waveguide walls that will allow this to be sort of a broken loop, if you will, right?
E phi here.
This one is E phi, yeah. This one has a combination of rho and phi, but no Z, right? But if it can be open loop and closed loop. In closed loop, it has to be completely tangential to the metal because the boundary condition that the normal component of D has to terminate on charge. But there's no normal component in this, so this is okay. And this one, you can have open loops, but then it has to have this boundary condition N dot of D equal to rho S. So this also comes back to this confusion of a chicken and egg, if you will. Here we have these modes that we derived by solving the wave equation and applying to boundary conditions. And from those field patterns, we can use boundary conditions to find surface currents and charge distributions, right? But then there's the question of, well, if there's surface currents and charge distribution,
Use that.
if there's surface currents and charge distribution there, then how did these solutions apply there? Because these were for the homogeneous wave equation, and this is in the presence of sources. But these are induced sources, right? We use the fields and we say what currents and charges are associated with this field pattern. Or if you want to do it the other way, you would start with the current and charge and solve an inhomogeneous vector wave equation that has right-hand side not equal to 0, and you'd use vector potentials, find the radiation, and confine it to the waveguide walls with boundary conditions, and you should get the same E and H. Okay.
So in DE01, there is no surface current in either surface charge.
TE01 here?
Yeah.
Yeah, how can there's no surface charge, right?
But what about surface current?
Yeah, there is surface current, right? The surface current, that's a great question, as a matter of fact, because let's understand that. So the magnetic field here is going to have a tangential magnetic field because these loops that are going like this,
H is J.
these are going through down the waveguide and then coming back, right? That's a bad picture, but if you were to look at this TE01 mode in this direction, the magnetic field looks to me like it's doing this, right? So there is tangential H. There will be surface current, but why?
Because surface current is in wrong direction, and we have H rho N cross H, which is rho cross no.
So this electric field it looks like it's purely azimuthal. Let's go back and look. We can find out right now, right? So That was a TE mode, right? These are TM modes, I think. So let me go back. Yeah, so now we're doing some cool fun stuff here, investigation. Here. This is TE modes. So TE,
Yeah,
is this TE? This is TE, right? Yeah. What mode are we talking about? 0, 1. All right. So 0, 1 comes from this Bessel function, as a matter of fact. But that means that this is equal to 0. Yes, 0. That's right. So sine of 0, this is 0. Okay, that's fine. This is normal component, though. It doesn't need to go to 0. But this becomes cosine of m phi. So the azimuthal variation is cosinusoid, right? It's m0, it's m is equal to 0?
zero is 0.
TE 0, 1, right? So, and this is m. So that means m is equal to 0. So there's no azimuthal variation. Makes sense. It's a perfect circle, right? In azimuth. All right. But E rho at, let's say z equal to 0. So let's get rid of that. This all goes away. Then we have m equals 0. Yeah, there is no rho, right? So that means that it's purely azimuth, yeah? And exactly, purely azimuthal. And at m equal to 0, t 0, 1, there's no azimuthal variation. So this doesn't go away. Excuse me, this goes away because m is equal to 0, but this just becomes cosine of 0, which is 1. So it's phi independent. So it is a ring in phi. It has phi component only, and it doesn't vary it does vary in rho, though. So at rho equal to a, what do we know E phi has to be? 0. So if it looks like this, then we have sort of a strong field here, and it gets weaker, and then it becomes 0. So if you plot the strength here, let's see, what is J0 starts out at 1 and goes to 0. So it probably looks like that. Depending on what beta rho is, right? If beta rho is high, it might oscillate. So it could be something like this, but
0 on the boundary condition.
yeah, E phi has to be 0 there. So that's super interesting, right? So the boundary condition here is, and as you go along Z, that thing's gonna go, it's gonna be, let's see, as you go along 0, it'll be a maximum. If you look down the waveguide, it'll be a maximum, and then somewhere it's gonna go to 0, so you have basically no electric field. Then it'll go probably the same thing down here. So it'll look sinusoidal in this direction, right? There should be a 0 here, so it should go like that. Okay. What is our question? How do the boundary conditions apply here? So we have surface current, right? We have H.
HZ does the contribute to the surface current.
HZ does, yeah. So, but okay. So what are we trying to say? We're saying that yes, there's a surface current, so there must be charges on the walls of the waveguide. Why is the electric field not terminating on them?
But there is current or there is no surface charge.
There's current for sure.
Current is in phi direction.
The current's in the phi direction.
Yeah, because M hat is rho hat and HZ rho hat cross Z hat would give phi hat. So
Yeah.
A is phi hat. Circulating.
What about rho cross phi?
Phi is 0 because M is 0. H phi is 0.
Where's A? Why is H? Oh, M's. Oh, good. So there's only HZ, and N cross HZ gives you phi. Yeah, that's probably what it is, right? The electric field has to go to 0 there anyway. So the charge is, okay, very nice. Very good. So yeah, there's current. It's azimuthal current though, right? And if there's azimuthal current and the electric field has to be 0 there, but the normal component could still terminate on that, right? Why isn't there an electric field with a normal component? Oh, but there's only E phi. Okay, yeah. There's no E rho there for that mode. That's an interesting mode, actually, as a matter of fact. Very cool. So, yeah. So that's the first time that I can say that I've seen current, but no electric field terminating on those charges. This is a cool, it's an interesting case. All right, good. So we're done here, right? 5:15. Let me see what I got here real quick. There's only this last slide. Let's just do it really quick. So this is just a couple pictures. This is the last slide. We have excitation of TE11 mode. We can put 2 of these probes in here like that, and we can excite the TE11 mode. If you go back to the distribution of the TE11 mode, then this is one way to do that. Excitation of TM01 mode, you can use a probe like this, and so basically you need to put this field in the where the electric field is maximum for these modes, right? You can use a waveguide, a rectangular to a circular waveguide transition in order to excite a particular mode, or you can use to excite the TE1 mode. We'll come back to this and look at the mode plots because these won't make sense unless we look at the mode plots as well. All right, so let's do that. All right, start your homework as early as you can because you might get stuck somewhere and you need help, all right? All right, I'll see you guys. Good job.
Our team doing waveguides feel nice and comfortable now.
Thank you.
All right, have a good one.
As much.
We're gonna talk about all of these.
Where's the principal?
You guys have homework to do?
Yeah, okay, good. Let's take a look at you have the, let me send you those notes, but I could probably pull them up on here. Let's take a look. I think there is a class in here after, so I'll show you what I got real quick, and then I will send you these slides as well, right? So let's go here, and that's gonna be 6, I believe. Okay, so in here, what do we have? So the whole thing is we don't know how to solve directly the electric and magnetic field given the sources J and M. You can try to do that if you take this path. And what you find is if you try to derive a wave equation by keeping the right-hand side not 0 with a current density, then you're going to end up having to differentiate that current density somewhere on the right-hand side. And what's difficult about that? Well, to solve this wave equation for arbitrary J, what you want to do is exploit the linearity of the wave equation, Maxwell's equations, and solve for a delta function first. And then you can use spatial convolution with that solution. Yeah, do you take linear systems before?
Signals and systems.
Yeah.
Continuous and
Do you remember what an impulse response is?
Yeah.
So we couldn't solve the linear time invariant systems differential equation directly for x of t, but we solved it for delta of t. And what we got was h of t, right? And then to find the solution due to y of, or x of t, to find the y of t, we did the convolution of h of t minus tau with x of tau, right? And we integrated. We do the same thing here.
Yeah.
It's all based on linearity. But on this side, to find the solution to this differential equation given a delta function on the right-hand side in place of the source, you have to differentiate a delta function, which gets kind of difficult to do. So what you can do instead is take this auxiliary path where you calculate first what's called a vector potential, and then you can differentiate that vector potential, right? The difference between the wave equation to derive in terms of vector potentials directly from the sources and that of electric and magnetic fields directly from the sources is that the right-hand side where the source is just becomes mu j.
Right.
And that means you can differentiate, or you don't have to differentiate a delta function. All right. Okay, so we define h as 1 over mu the curl of A, right? That's the definition we choose. But we have to ensure that our definition is chosen such that this potential satisfies Maxwell's equations, right? So here we have the divergence of B. We're going to check all Maxwell equations one at a time. Here we have divergence of B is equal to 0. Well, B we've defined as the curl of A.
Right.
So the divergence now of B equal to curl of A is the divergence of the curl of A, and that equals to 0. By definition, the divergence of the curl of any vector field is 0, and divergence of B has to equal to 0. So we've satisfied Maxwell's magnetic Gauss law with this definition. Faraday's law now, we can check that. Curl of E is minus j omega mu h. But we know what h is. H is 1 over mu curl of A. So substitute that in. And then we have the curl of E is equal to minus j omega curl of A. And because the curl operator distributes, we can move this curl of A to the other side. and we have the curl of E plus j omega A equal to 0. But this is cool because, as I was saying before, if the curl of some vector field equals